Well, today I want to show you a couple of examples of how you can use this residue theorem to calculate integrals. And these are just integrals that you could write down in a beginning calculus course. So these are integrals of real variables. But the methods are kind of cool in that they go via integrating some complex function on some simple closed curve and then using the residue theorem. So let me just show you a couple examples. These are like similar to the first two examples that the author does in the book. So you can look at them, and then you can look at these for a couple other examples. So the first example is the easier one. Suppose you want to do this integral. 0 to 2 pi d theta over 13 plus 5 sine theta. Right? So you could pose this problem in Calc 2. You could actually do it by methods that can be introduced in Calc 2, but it's a little nasty. This is a much more elegant method. And the method I'm going to describe, this function could be any rational functions of sines and cosines. So any ratio where the numerator and denominator are put together by taking powers of sines and integer powers of sines and cosines and adding, subtracting, multiplying by constants, and so on. So how do we go about this? Well, this integral, the limits kind of, and the d theta kind of remind you of when a few times in the past where we've parameterized a circle, z equals e to the I theta. So here's the unit circle. Z equals e to the I theta running from 0 to 2 pi, and dz is I e to the I theta d theta. So d theta is dz over I z, that's this. And the sine of theta, remember sine theta is e to the I theta minus e to the minus I theta over 2i. So that this is z, this is 1 over z. So it's that. Substitute all of this into here, and it turns into this. It's almost like I'm going backwards. If I started from here and I said do this line integral, you would say, well, let's parameterize z by e to the I theta, and if you went through the manipulations, you get back to this. I'm going the other way. Why? Well, because here, after a little simplification, I can use the residue theorem. So here I just basically, what do I do here? I just I add these, put both of these terms over 2i and gets this, and then the iz I bring down. These i's cancel. This 2 goes up there, leaving me a z times this, so 5z squared, 26zi, and a minus 5, which I can factor like this. So now this is a line integral of dz over this function of z, and the integral is taken over the unit circle. Where are the singularities? Well, you see from here, it's this one in minus I over 5, and here is minus 5i. So in terms of the unit circle, singularities are here and here, right? But in terms of this integral, the only thing that matters is the singularity inside the circle. So that's just this one. So this integral, well, there's the 2. Then this integral will be 2 pi I times the residue right there. So I got to calculate this residue. This is a simple pole. The residue will be gotten by taking the limb as z approaches minus I over 5, z minus I over 5 times this function. See, this guy and this guy almost cancel, except for, they're the same except for a factor of, this guy and this guy are the same except for a factor of 5. So if I factored a 5 out of this, I'd be left with z plus I over 5. You see, and it would cancel that. So that's what I've done here. These cancel except for that 5. And when I plug in z is minus I over 5, I get that. And then multiply multiplying by 5, I just get this, which is 1 over 24i. I plug that in here. 2 times 2 pi I times 1 over 24i, and I get pi over 6. Notice that the i's disappear at the end, as they must, since we started out with a real integral, so the answer has to be purely a real number. And it is. Right, so there's a number of problems in the book of this nature, and they're handled roughly like this. You make these substitutions, turn sines and cosines into things involving z and 1 over z, do the algebra, find the singular points, calculate the residues, etc. So that handles ones like that. The second one I want to describe today is a little more complicated, and that is this one. So this is an improper integral. Integral 0 to infinity, dx over 1 plus x to the 4th. Now again, you could solve this by Calc 2 methods, but you have to factor 1 plus x to the 4th into the product of two quadratic terms. And then you could use partial fractions and trig substitutions and so on, and eventually get an answer. But here we're going to do it with complex methods. Notice, of course, by symmetry, this is half of the integral from minus infinity to infinity. So I'm basically trying to integrate over the real line from minus infinity to infinity. So here's what I'm going to do. I'm going to think of integrating from minus rho to rho. Rho would be the radius of some circle. Think of rho as fairly large. Eventually it's going to go to infinity. So I'm going to create a curve, a C rho, in two parts. It's going to be this interval from minus rho to rho, and then this semicircle that takes me back to minus rho. So C rho is this closed curve. And I want to think of rho as large. And eventually we'll pass to the limb as rho goes to infinity. All right, so now let's change the x's to z's, and let's consider this integral. So I'm integrating this function 1 over 1 plus z to the 4th over this simple closed curve. So by the residue theorem, it's 2 pi I times the sum of the residues. Well, what are the singularities? Where 1 plus z to the 4th is 0, so the solutions of that will be the 4 fourth roots of negative 1, which would be at these 4 places, corresponding to angle pi over 4, and then 3 pi over 4, 5 pi over 4, 7 pi over 4. Now you noticed, so they're the singularities. And you noticed 2 of them are inside C, and 2 of them are not. So I just need the residues here and here. So that's what we have here. This is 2 pi I times the sum of those two residues. Again, these are simple poles, and the residues are calculated. How? Well, again, I'm going to multiply, say for this one, at the point e to the I pi over 4, I'm going to multiply z minus e to the I pi over 4 times my function, and I need to calculate the limb as z approaches that. See, both of these go to 0. Both of these go to 0 as z approaches I pi over 4. What about the ratio? The easiest way to do it, I mean, you could try to factor this. You could factor this, which would be fine, but the quicker way to do it is just use L'Hopital. And I can just differentiate, because both of these go to 0, so I differentiate top and bottom. Up top I get 1, down below I get 4z cubed, and I take the limb as z goes to that. So I basically just plug in, once I've done this, I plug in z equals e to the I pi over 4. It becomes cubed, so it's e to the I 3 pi over 4. In the denominator, so that's the same as e to the minus I 3 pi over 4 in the numerator. So the first residue is that. Play the same game for the second residue here, 3 pi over 4 times I. multiplied by z minus e to the I 3 pi over 4 over 1 plus e to the fourth. Use L'Hopital, and then plug in, use L'Hopital, which gets me again to here, and I plug in e to the I 3 pi over 4, and I get that. So that's e to the I 9 pi over 4, which is the same as pi over 4, because that's 2 pi plus pi over 4. So that's the same as, this guy is the same as e to the I pi over 4, and in the numerator is e to the minus I pi over 4. So the residues are this and this. So they really just correspond to really essentially these two values down here, right? Because this is e to the minus, this one is e to the minus pi over 4, and this is e to the minus 3 pi over 4. And there are their values, right? They're both basically square root of 2 over 2. They're both x and y coordinates are square root of 2 over 2 with, well, this one they're both negative. This one is positive and one is negative. So when I add these, the real parts cancel, the imaginary parts add, I end up with this. So the sum of the residues is that, and then I multiply by 2 pi I over here, and I get this number. So where have we gotten to? What we found is that the line integral along this curve, this simple closed curve, as long as rho is at least 1, as long as rho is bigger than 1, so that the curve encloses these 2 points, right? But I'm always assuming rho is big, so this will be true. So I get that this integral is this by the residue theorem. And you see this answer is completely independent of rho. It doesn't matter how big rho is. Once it's big enough to contain these two residues, the integral is that. But now let's actually think of doing the integral. The integral is 2 pieces, this piece and that piece. So on the real line, from minus rho to rho, just let z equal x. dz is dx, and you just get this usual kind of basic calculus integral. And as rho goes to infinity, this goes to the improper integral we're interested in. That's this improper integral. So that's where it's coming from. But what about the other piece? So along the semicircle, z is rho e to the I theta. So dz is I rho e to the I theta d theta. When you plug everything in, you get the integral from angle 0 to pi. Here's the dz, and this is 1 plus z to the fourth. Now, we don't want to do this integral. It'd be ugly. But all we want to do is think about what happens as rho goes to infinity. And the beauty is that this integral goes to 0. Why? Well, if you think about just norms in terms of the norm of complex number, remember e to the I theta or e to the I 4 theta, they're just complex numbers of norm 1. So in terms of norm, the guy in the numerator basically is like rho. And the denominator is like rho to the fourth. So basically, in terms of the norms, it's like rho over rho to the fourth. So it's like you can factor out a 1 over rho cubed. But then as rho goes to infinity, that, of course, will go to 0. And so we never actually have to do this integral, because as we pass to the limb, it goes to 0. So where are we? The actual value of the line integral doesn't depend upon rho. As long as rho is bigger than 1, it's always the same. It's always this number. But if we let rho go to infinity, of course the integral stays this, but it's in 2 pieces. The one piece tends to this improper integral from here. The other piece tends to 0. So these two together tend to just this improper integral. And therefore what? Taking the limit, we find that this guy is square root of 2 over 2 times pi. So our original problem was half of that. The original integral It's half of that, so you get this as an answer. So here's the subtle part of this, observing that this part of the thing, the integral over this semicircle, tends to 0. And what made this argument work is basically this condition. I mean, we had a simple case here. Think of it as like a polynomial over a polynomial. Of course, here the polynomial up top was just 1, the function 1. So the polynomial up top has degree 0. Polynomial on the bottom has degree 4. So here's that 4. We get a row here from differentiating. That comes from the dz. But so if we just have a ratio of polynomials, as long as the degree on the bottom is at least 2 more than the degree on the top, the same argument will work. Because if this has degree 2 more than this, then when we go here, we get an extra row up in the numerator from dz. But since the denominator is 2 more, even when you add 1 to the numerator, the denominator will still have more rows in it than the top. It'd be like a row cubed over a row to the 4th. And that will still go to 0 as the row goes to infinity. So this method will work, and this part of it will go to 0 in the situation where we have a polynomial over a polynomial. The degree of q is at least 2 more than the degree of p. And, important, of course, this whole argument would sort of fall apart if we had singular points on the real line. Right? My 4 singularities are off of the real line. So I don't need to worry somehow like I'm trying to integrate directly through a singular point. And that's because I'm assuming the denominator has no real zeros. For us, the denominator was 1 over x to the 4th, and the solutions of setting that equal to 0 were these 4 points. None of them were real. They all had an imaginary part. So if you look in the book, you'll see she makes these same observations. This method will work for anything involving this. Again, in theory, problems of this nature could be handled with partial fractions, but it would be, assuming you could do the factorization, but it would be pretty nasty, and this is a very elegant way to do it. So these are 2 of the, believe it or not, these are maybe 2 of the simpler examples. And in the next video, I'll go into some more complicated examples, but this could at least get you started on trying to understand and work out some of the simple examples. So I'll stop.